Welcome back to my office hours. Today we will talk about the application of the principle of manometry. In our previous video, we have discussed the use of hydrostatic equations for calculating the hydrostatic pressure at any given elevation in a fluid. When using hydrostatic equations, particularly the algebraic equation, it is critical to note that the specific weight of the fluid must remain constant. In other words, the algebraic equation is only applicable within one single fluid phase. When two or more fluids are involved, we have to write multiple hydrostatic algebraic equations in order to calculate the pressure change across these different phases. Each hydrostatic algebraic equation is for one fluid phase only. As more fluids get involved in this type of calculation, the solution can be tedious and time-consuming. Can we have a method that is more efficient? Surely yes. After learning the principle of manometry today, you'll love this method, I guarantee. A manometer is an instrument used to measure and indicate pressure. There are two types of manometers, analog and digital. The most basic and simplest form of an analog is the U-tube manometer, a glass or rubber tube bent in the shape of a U, where numbers are listed and spaced every inch on each side, and manometer liquid is placed in between the bends of the U. When pressure is applied, the manometer liquid moves to indicate the pressure behind it, expressed in inches of manometer liquid column. The link between the manometer liquid column height and the pressure can be derived from the hydrostatic algebraic equation. For example, if we know the pressure at section 1, and we need to know the pressure at section 2, and we know the elevations at these two sections are Z1 and Z2, respectively, what would be the pressure at section 2? Writing the hydrostatic algebraic equation and solving for the pressure at section 2 derives P2 equals to P1 plus the specific weight of the liquid multiplied by Z1 minus Z2. Because Z1 is larger than Z2 in this particular example, Z1 minus Z2 is the elevation difference delta Z between the two sections. Therefore, the pressure P2 equals to the pressure P1 plus the specific weight of the liquid multiplied by the elevation difference delta Z. During this process, the elevation goes down in the manometer liquid as we move from section 1 to section 2. Let's try to do it again. But this time, let's say that we know P2, but we don't know P1. As we work on the hydrostatic equation, we find that P1 can be calculated using the pressure P1 minus the specific weight of the liquid multiplied by the elevation difference. This time, the elevation increases in the manometer liquid during the process as we move from section 2 to section 1. With these two examples, we can summarize the principle of how to find the unknown pressure from a known pressure. To find the pressure of the unknown in a manometer, we will start a journey from the known pressure section to the unknown pressure section, find the product of specific weight of the manometer liquid and the elevation change delta Z. If the unknown pressure is at a lower elevation in the liquid, we will add the product to the known. If the unknown pressure is at a higher elevation in the liquid, we will subtract the product from the known. If there are two fluids in the manometer, we will now need two sets of hydrostatic equations, one equation for each liquid. In each liquid, we will apply the same principle as the one we previously derived. For example, if the pressure at C is known, and we need to find the pressure at D, we will make a journey from C to A in the yellow liquid, then from A to D in the blue liquid. We ignore the stop at B, because A and B are in the same liquid and their elevations are the same. According to hydrostatic equations, the pressures at A and B are the same. For the part from C to A, we can use one hydrostatic equation to find pressure PA represented by pressure PC. For the part from A to D, we can use another hydrostatic equation to find pressure PD represented by pressure PA. As we substitute the pressure PA from the first part, we can see that the principle of manometry has been verified. If there are more fluids in the manometer, the same principle applies. We will discuss this example in another video through step-by-step explanation. Stay tuned for the update. Now let's summarize the principle of manometry. There are several fluids in a manometer. The pressure on one end is known as PA if we want to calculate the unknown pressure PB. We will start a journey from A toward B. During this journey, we make a stop every time there is an interface between two different liquids. If the elevation has decreased during this part of the journey, we will add a pressure change, which is calculated using the specific weight of this involved liquid and the elevation change. If the elevation has increased during this part of the journey, we will minus a pressure change calculated in the same way. Afterwards, the journey continues, until we arrive at our final destination B. Can you solve for the pressure at the center of pipe in this problem now? Notably, we don't even have to have a U-shaped manometer to use the principle of manometry. In a regular water container, such as the one shown here, the principle of manometry is also applicable. Why don't you give it a try? Thanks for watching. Don't forget to leave a like or subscribe for future updates.